developed world, the following happens. Let us watch this beautiful sunrise first. The sun sends short wavelength, high energy solar radiation towards the Earth. 32% of this radiation is reflected, either by clouds, 21%, dust, 5%, or water, 6%. Only 1 to 2% is used by trees and other plants for photosynthesis. The remaining 67% of the radiation reaches the Earth and is transformed into heat. That's the same as infrared. This infrared radiation passes up into the atmosphere, but instead of being radiated 100% back into space, much of it is absorbed by the atmosphere and re-radiated to the surface. This is what we call the natural greenhouse effect, and occurs because of greenhouse gases that are naturally in the atmosphere. This phenomenon keeps the planet at a nice 14 degrees Celsius. If this wouldn't occur, the planet would have an average temperature of minus 17 degrees Celsius. But now, a disaster happens. Man. Because of cars, factories and intensive agriculture, more greenhouse gases accumulate in the atmosphere. Let us watch the sunrise. Again, the sun sends her short wavelength, high energy solar radiation towards the Earth. 32% of this radiation is still reflected by clouds, dust and water. 67% is still changed into heat by the Earth and radiated back into the atmosphere. But this time, the large amount of greenhouse gases reflects more of that heat to the Earth, leading to a temperature rise, with all its disastrous consequences.
Now, the solar system together is electrical. The electrons, which are negative, are attracted by the protons, which are positive, and vice versa. But here in the nucleus are other particles with no electrical charge, called neutrons. Very important characters, too, as we shall see. And equally important when it comes to atomic energy is what scientists call the atom's binding force. It's a kind of cosmic glue holding the nucleus together. This, then, is a single atom, but certainly not all atoms are alike. There are in nature more than 90 basic elements, which is science's term for families of atoms. To scientists, the atoms of the individual atom families, or elements, are identified by number, that is, the number of protons or positive charges in their nucleus. And they vary all the way from hydrogen, which has just 1 proton, to oxygen with 8 protons, to gold, he's rich with 79, finally on to the heaviest of all natural elements, uranium with 92 protons. Now, within each element or family of atoms, there can be different members, each one having the same number of protons, but differing in the number of neutrons. The total of an atom's protons and neutrons is its atomic weight. Thus, in natural uranium, we have U-234, U-235, and U-238. These different members of the same element or atom family, science calls isotopes. Some elements, tin for instance, have a great many isotopes. Others, like aluminum, are lone wolves with just 1. Now, most atoms of most elements are content with their lot in life. We speak of them as being stable, but others are busy day and night, being what science calls radioactive. Like radium, throwing off powerful rays along with some of its neutrons and protons, until it actually alters its own nuclear structure and changes to another family, and then to another, until it does become stable at last. This spontaneous changing of elements is called natural transmutation. Its discovery gave men of science an idea. If an atom could change itself, why couldn't man change an atom? Using as bullets the very particles which radium threw off, a noted British scientist bombarded nitrogen and converted it to oxygen. In terms of individual atoms, this is what happened. The radium nucleus threw off an alpha particle consisting of 2 protons and 2 neutrons. One of the protons was absorbed into the nitrogen nucleus, turning it to oxygen. This was artificial transmutation, man changing the elements. From that first experiment, others by the thousands followed as scientists devised ever more powerful particle accelerators, commonly called atom smashers, to transmute more and more kinds of atoms. All scientifically important, but hardly world-shaking. Then, in 1939, some scientists were experimenting with transmutation of uranium. What would happen, they wondered, if they fired a neutron at a uranium nucleus, already the heaviest in nature? Why not try? So they tried. And the result? Nuclear fission. Instead of a minor change, the atom split in 2. Truly a discovery to change the world. For what had happened when the uranium atom split was a kind of double miracle of science. Half of the miracle concerned that binding force we spoke of before, that kind of cosmic glue which holds the atom's nucleus together. We still don't know all about that binding force yet, but we do know it is equivalent to mass. Therefore, we may speak of it as having a kind of weight of its own. Now, the 2 atoms into which a uranium atom splits also have binding force. But for some reason, it takes less of that glue to hold them together, and in the process of fission, a tiny fraction is left over. What happens to it? It explodes as energy, proving Einstein's theory that mass and energy are really the same. But we spoke of a double miracle. To understand the second one, let's slow down that fission 1 million or so times. A single particle starts the reaction, splitting the uranium atom. Here now is the release of energy as heat and blast. Here are powerful rays being given off, similar to X-rays. But here are free neutrons driven out with tremendous speed. And provided there is sufficient U-235 present, what science calls a critical mass, those neutrons bombard other uranium atoms, causing them to split and split still others. The result? A chain reaction. Over 1 million billion atoms exploding within 2 seconds.